Okay, everything's working. Good. There we go. Okay. So this is low solubility. So that means that there are 3 that are low solubility.
And it's wrong. Well, the answer key says B.
The answer key says B? Oh, are considered soluble. I'm sorry. I'm reading the question wrong.
C would do it.
Yeah, it should be 1 is considered soluble. I was reading I don't know. I was reading it wrong. There we go. 1 is considered soluble. That one is soluble. Okay. Next one on our list is 61. In which of the following would AgCl be the most soluble? So we want something that will shift this furthest to the right. Will adding HCl shift it to the right? If we're adding HCl, we're adding H plus and we're adding Cl minus. Will adding H plus do anything? No. Will adding Cl minus do anything? Yes. Which way will it shift it? It'll shift it to the left. Is that any good? No, because we want it to shift to the right. How about Ag plus or NO3 minus? Does NO3 do anything? No. Does Ag plus do anything? Yes, but it shifts it left. So that's not what we want either. MgCl2 gives us more Cl. And we already agreed Cl shifts it to the left, so that's not it. It has to be our last one. NH4 does nothing. NO3 does nothing, and nothing makes it more soluble than these other ones, which are all shifting it to the left. So the answer is D. Next one is 65. Yes, sorry. Adding solid does nothing. Yeah, adding water does nothing. Not to the solubility. You'll dissolve more, but you'll also have a bigger volume. So the concentration will remain the same. Yeah. Okay, 65. A solid piece of magnesium carbonate is placed in water while the solution is unsaturated and the solubility equilibrium is being established. You must be dissolving faster than you are recrystallizing. So the rate of dissolving is higher than the rate of crystallization, because that's the only way the concentration will continue to increase. Okay, number 78. We have the KSP. Yeah, sorry. Oh, gotta go back. There we go. '78. KSP for cadmium carbonate is 1 times 10 to the negative 12. What is the solubility? If this was a written response question, you would do all the stuff like let the molar solubility equal X, blah, 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 blah. But because this is multiple choice and you know this is a 1-to-1 salt, you can say KSP is equal to X squared, where X is the solubility. That's our molar solubility. If it was a written response question, you would say this is X, this is X, this is X. You would write the KSP expression, blah, blah, blah. Throw that all in there. But what we're going to do is we're just going to say X is equal to the square root of 1 times 10 to the negative 12, which is that 1 times 10 to the negative 6? Does it work that way? I think it does. Yes, it does. Okay. I should know that. 1 times 10 to the negative 6, and that is in moles per liter. But we are given answers in grams per liter, so we would need to multiply by the molar mass of cadmium carbonate. Ugh. 12 plus 16 times 3 plus 112.4. 112.4 equals 172.4 grams per mole. And we get 1.7 times 10 to the negative 4. Next one is number 85. We have lead oxalate. What happens when we add some sodium oxalate? Well, we're adding oxalate ions. If that concentration increases, the equilibrium shifts to the left. And if it shifts to the left, then we have less dissolved stuff. And so the solubility will decrease. So the answer is B. Next is number 91. Solid KBr is added to saturated AgBr solution, AgBr. And we added some KBr, so we are increasing the concentration of Br minus. If we increase that concentration, it shifts to the left. And our concentrations, if this is Ag and this is Br, initially they're the same because we had our silver and our bromide. They were both from AgBr, so they are the same. And then our bromide ion concentration was increased. It shifts to the left, so we are now using up bromide. As we go this way, bromide's being used up, but it never gets down to quite where it was before. And the silver also, as we go to the left, silver gets used up, so it goes down. But the bromide ends up higher than before, and the silver ends up lower than before. So the answer is B. Next is 92. Solid strontium hydroxide is added to water. Which of the following is true for this equilibrium system? Does the concentration of the anion equal the concentration of the cation? No, because this has a 2. Is K trial less than KSP? That's not even something, no, that doesn't make any sense. We have prepared a saturated solution. I don't even know what that means. Blue litmus paper would turn red. Well, hydroxide is a base, and base turns litmus blue. So it's not going to turn it red. And we have a saturated solution. Does the rate of dissolving equal the rate of recrystallization? Yes, because at a saturated solution, we are at equilibrium. So the answer is D. Next is 100. In which would we expect AgCl to have the lowest solubility? If it's the lowest solubility, we want it shifted furthest left. Well, pure water, no shift. If we increase the concentration of Ag plus, that shifts it left. If we increase the concentration of Cl minus, that's going to shift it left. Here we're increasing concentration of Cl minus. That's going to shift it left. And this one's going to shift it left. Oh no, they all shift it left. What are we going to do? Which one shifts it left the most? This one is 0.2 molar. Yeah? Barium chloride, because there are 2 chlorides, we get 0.04 molar chloride. So we have 0.2 molar silver, we have 0.2 molar chloride, because that's a 1-to-1 salt, and we have 0.015 molar chloride. Which of those will cause the biggest shift? Biggest concentration, biggest shift. So the answer is B. Yes, beta. For D, because it says it right there. Oh, yeah. If it was that, it would be D. Yeah, it should be 0.02. Yeah, that's my bad. I'm so sorry. Yeah. In which of the following would we expect AgCl to have the highest solubility? So in this case, we want this thing shifted to the right. Well, Cl will shift it left. Ag will shift it left. Cl will shift it left. So we're left with the pure water, which has no shift, which is not shifting it right, but it's certainly less to the left than with nothing. So it would be the pure water. This is almost the exact same question. In which of the following would you expect AgBr to have the lowest solubility? If we want the lowest solubility, we want it shifted most left. So we have 0.15 Br. We have 0.2 Br, 0.1 Br, and 0.1 Ag. So which one is the biggest? That's going to be B. That's our highest concentration of Br. We'll shift it the most to the left. By the way, what do we call this effect where we're adding either the Ag or the Br? That's called our common ion effect, where we add an ion in common and it shifts it to the left and it decreases the solubility. That is our common ion effect. All right. (103, 104). In which of the following would you expect AgBr to have the highest solubility? Oh, look, we have a common ion, common ion, common ion, common ion. Those are all going to make it less soluble. And so the answer is going to be, it's going to be the most soluble, highest solubility in pure water. And I think 104 is the same kind of a deal. Lowest solubility, you want the highest concentration of ion. So that would be this one. There we go. And that's it. Nobody else has asked any other questions. So does anyone have any other questions? Yes? Sorry? 116. All right. 113 and 16. Yep. Let's do 113 because we're on our way. Let's go in order. 113. What is the maximum concentration of chloride ions that contains a 0.1 molar lead? So we know the concentration of lead, and we know that KSP is 1 times 10 to the minus 4. So we have lead chloride. And our KSP is going to equal lead times chloride squared. We know our KSP is 1 times 10 to the negative 4. We know our concentration of lead is 0.1. And so we can solve for chloride squared. Which is 1 times 10 to the negative 3, I think. And that means concentration of chloride is 0.032. So you are given KSP, you're given lead, and they're like, how much chloride can have can I have in solution? For it to stay in solution, it needs to not be any bigger than what would give us our KSP value. And so if we make that equal to KSP and then just solve for chloride, we can have that much that would just barely saturate it. And if we had any more, it would start precipitating, but we can have up to that much. Did I just guess? What? Oh, so I took my KSP value here. I took the lead that was given in the question. Yeah, that came from, all of that came from the question. And then we just solved for Cl2, 1 times 10 to the negative 4 divided by 0.1. Yeah? Cool. Cool, cool. Okay, and now 116. What is the solubility of lead chloride in a solution of 0.15 molar HCl? Thank you. So once again, we are given KSP. And we are given the concentration of Cl. Same as HCl, yeah? And that means we can solve for the concentration of lead. So we have 1.6 times 10 to the minus 5 divided by 0.15 squared gives us 7.1 times 10 to the negative 4. Now, that also means that you're going to have a little bit extra chloride, but nothing compared to the 0.15. So what we've got really is we've got PbCl2, Pb2 plus 2Cl minus. And if we say, okay, we have 0 here, we have 0.15 here. This is our initial. Our change in concentration, this is going to be plus 2x. This is going to be plus x. Yeah? And our equilibrium concentration is going to be x. And 0.15 plus 2x. But this is a really big number in terms of solubilities. Low solubility compounds usually are producing times 10 to the minus 4, times 10 to the minus 5. Those are all very small. So we can assume 2x is insignificant. So what we have then is we have lead, which is x, and we have the chloride, which is 0.15 squared. And those are the same. That's just kind of showing it with a rice table, if that's helpful. Because it's a multiple choice, I wouldn't bother with the rice table. I'd just like assume that the concentration of chloride is all from the, you know, sodium chloride or whatever it was, HCl, all from the hydrochloric acid. And then, yeah, did that make sense? Yeah, okay. Does anybody else have any other questions? Okay, whatever time we have left, you can just work on your review. I'll get quizzes back to people if you wrote it last week. And yeah, I think that's it. Okay.
Oh my God, you need a pencil. Are you sure you didn't have a pencil crayon?